Hello everyone. Today we want to talk about how we would determine how much magnesium ions and calcium ions are present in seawater. So our goal is to determine how much calcium and magnesium ions in seawater we have, and the concentration is very low. So this method of edta titration is a very powerful technique to determine the concentrations of ions in a sample where the concentration is very low. So what skills will we develop in this experiment? Well, we will develop expertise in using the burette. You've used the burette before in the acid-base titration experiment, and we will also have experience in the determination of an endpoint. We are going to be using different indicators in this experiment than we did in the acid-base titration. What knowledge will we gain? Well, we will have an understanding of how to determine minute concentrations of ions in a sample. We will understand some of the characteristics of the chelating agent, edta. So chelate means claw. So this edta reagent will grab onto ions like a claw. And we will also extend what we know about error determination. So we've done acid-base titrations before. This is a different type of titration, but all titrations involve the following characteristics. A chemical reaction goes 100% to completion, so all of the reactants are used up and we form products. So one of the reactants is in the burette, so we call that the titrant, and the other is in the flask. And all of the reactants are converted to products. So the other thing that we need is we need a method, usually a color change, that indicates when the equivalence point has been reached. And what we mean by that is that all of the reactants have been converted to products, sorry. There are no reactants left over, no reactant is in excess. So the exact amount of reactants have been added so that we have all products and we have no reactant in excess. So this is an edta titration, so that's our titrant, and the structure is shown down here. So this edta stands for ethylene diamine tetraacetic acid. So these are the acetic acid groups right here. So it is an acid. It's tetraprotic, and what that means is that there are 4 dissociable protons, which I've underlined here. So if we take off each one of these protons, then we would have negative charges at each one of these carboxylate groups. So in this fully protonated form, we can just call this H4Y, where we designate Y is the entire molecule, and then these are the 4 protons that can dissociate. So in solution, maybe some of the protons dissociate, maybe all of them don't dissociate. But when the protons dissociate, that gives the edta an opportunity to form this complex with magnesium and calcium ions. And this is what the complexes look like. So if we have our edta right here, and this shows the 1, 2, 3, 4 protons right here. But if the protons dissociate so that we have the negative charges, then the calcium ion right here, which has a 2+ charge, is able to form bonds with the edta, and 2 of them are with the negatively charged carboxylate group, and the other 2 are with the nitrogen. So we have a calcium edta 2- complex. So we have a calcium is +2, and then these are each -1. So we have overall the complex has a -2 charge. And with the magnesium, it's the same thing. And the magnesium forms the complex with the edta in a very similar way. So here we show that the calcium and the magnesium ions, when presented with the edta in the Y4- form, so this is when the protons have dissociated, can form this calcium Y2- or magnesium Y2- complex. So these are equilibrium constants, and we haven't gotten to this in class yet. This is a K of formation. So what we should note right here is that when these K values are very large, that means that the reaction goes to completion, and these are very, very large Ks. So that means when we have edta and calcium, we will form this calcium edta complex, and we have edta and magnesium will form the complex. So you won't have any free ions or any edta left over. You've completely formed the complex, and we can tell by looking at these really large Kf values. So again, the large values of the Kf means the reaction will go to completion as long as the EDTA is in its unprotonated form. So this Y4 minus means that the EDTA is in its unprotonated form. So we say H4Y when the protons are there, but when we take off the protons, it's in the Y4 minus form. So we want to make sure that that happens. So we could add a very basic buffer, pH greater than 12, and that will make sure that all of those protons have dissociated. But in this titration, in the second part, we want to precipitate magnesium ions as magnesium hydroxide. And we do that because we want to leave the calcium ions behind so that we can just determine the concentration of the calcium ions. But if the pH is too high, then that precipitation doesn't occur. So what we're going to do instead is we're going to carry out the reaction at a basic pH, yes, but not quite so basic. So say pH around 10. And here, instead of having the Y4 minus, we have HY3 minus. So what that means is these 1, 2, 3 protons come off, and that proton is still there. But remember from the diagram I showed you before, that's not involved in the complex anyway, so it doesn't matter. So we have this HY3 minus complex, and again, if we add either calcium or magnesium ions, we will get this complex. And the Kf values aren't quite as large, but they're large enough, so we know that this reaction will go to completion. So again, we can add the EDTA and we can have the EDTA react completely with the magnesium and the calcium ions that are in our seawater sample. But EDTA is colorless, magnesium is colorless, the calcium is colorless, the complex is colorless. So we have to find some way of figuring out when we formed our complex. So we're going to use an indicator called calmagite, and calmagite is blue. I don't know if you can see in this bottle right here, this picture I took, but this is a blue indicator. And calmagite also has dissociable protons. So here, the person, the artist who drew this figure wrote this as H3IN. So IN stands for indicator, and again, that's the whole molecule plus the 1, 2, 3 protons that can dissociate. So that's the indicator we're going to use in the first part. So in this flask right here, I have the seawater sample and the basic buffer that gives us the pH around 10, and then I added a few drops of the calmagite. So the calmagite, again, is blue, but as soon as it hit this flask, the flask turned pink. So what happened there is in the seawater, I had calcium and magnesium ions. So here we just say M2 plus M for metal. So those are the calcium and the magnesium ions. And when they encounter the indicator, so here the indicator is IN3 minus. So that means that all 3 protons dissociated because I added this basic buffer. And then what happens instantly is that the metal ion will form a complex with the indicator. So this is MIN minus, so that's the metal with the indicator complex. So it forms what Dr. Breen wrote in our manual as wine red. I think maybe it looks a little bit more like a rosé, but anyway, so you can see this nice pink color. So you add the blue indicator and immediately the reaction occurs right away. The metal ions bind to the blue indicator and they form a pink indicator metal complex. So now we're going to start our titration. So we're going to add the titrant to the flask. And what happens here is we start out with the, this shows magnesium, but calcium does the same thing. Our metal ion indicator complex, and remember that was that red or pinkish color. And then we're going to add the EDTA from the burette. So you should have seen from the slide that I just showed you that the EDTA is colorless. And then as soon as you add the EDTA, what happens is that the EDTA will displace the magnesium ion from the indicator and the EDTA binds it instead. So again, I don't have the Kf values for this, but I think they're like in the 10 to the 5th range. So what that means is that the EDTA binds to the metal ion more strongly than the indicator does. So it's really easy for the EDTA to kind of bump off the magnesium and grab it for itself. So now I have the magnesium EDTA complex. And what happens is when the indicator no longer has the metal ion, it turns blue. So as we do the titration, we're going to add the edta titrant, and as soon as we've added just enough titrant so we don't have any excess, and we go from this pink color to this blue color, that means we've completely formed our metal ion edta complex, and we just have free indicators. So there's no more metal ions bound to the indicator. Here's the picture right here. So again, I've repeated the same reaction right here. So all the metal ion is converted to this metal ion edta complex, and again, it's shown here as magnesium Y2 minus. And here it's a very pale blue, but you can see it really easily, especially against a white background. And it does go from pink to blue very quickly. So there's no doubt as to where the titration endpoint is. So at this point, we've added just enough edta, so that's our titrant, to knock off the magnesium ion from the indicator. So now the edta has the magnesium ion, and we just have free indicator, so it turns blue. So the other thing to remember is the paper that I got this from showed magnesium, but calcium does this too. So remember, in our seawater, we have both calcium and magnesium ions, and the edta binds to both of them. So in both cases, we have the edta knocking either magnesium or calcium ions from the indicator. And when we get to this blue endpoint, that means we have all free indicator, and we have edta in solution that has bound either magnesium or calcium ions. So if no calcium or magnesium ions that are free in solution, they're all bound to the edta, and we have just free indicator. So we have that blue color. So if we stopped there, that would tell us the moles of calcium and magnesium we have, but we want to make sure that we can figure out the concentrations of each of them separately. So the way we do that is in the second part of the experiment, we're going to precipitate the magnesium as magnesium hydroxide, and then we'll redo the titration. So what happens here is we have our seawater here, and this is, we add some drops of 50% sodium hydroxide, and that precipitates all the magnesium ions as magnesium hydroxide. So the calcium ions are more soluble, so they don't precipitate. So there's not a lot of magnesium in seawater, so you're supposed to get a white precipitate, but you might not see it very much. I think in this figure, maybe you can see that's a little bit cloudy, but there's not a lot of magnesium, so you might not see the magnesium hydroxide very well because there's not going to be that much of it. So we're going to use a different indicator this time. We're going to use hydroxynaphthal. So this is it's sort of a pink solid. So we add that to our flask. And this gives us a more intense color than the calmagite does. But the hydroxynaphthal has a chemical structure that's really similar to the structure I showed you for calmagite. So that means the same kind of thing is happening, that so we've precipitated out the magnesium ions, so they're not participating. So what's left is calcium. So the calcium now is binding to the indicator and forming that pink color. So we do the titration again with edta, so you can just use sort of the tip of my burette here. So we add the edta, and the same kind of thing happens. The edta will displace the calcium from the indicator, and the edta binds to the calcium itself because the edta binds to the calcium more strongly than the indicator does. And you'll see this, it goes from that pink color I showed you on the previous slide to a purple, but then one drop just gets it right to the blue color. So as soon as you get to the blue color, you know you have all free indicator and all the calcium is bound to the edta. And the magnesium hasn't participated at all because we precipitated it out. So the way we'll do the calculations then is that if we use the concentration of the edta solution that we find on the bottle and the volume that we used in our titration, so if a concentration and volume, we can figure out moles. And you can then look back at those equations and look at the mole ratio between calcium and magnesium and edta. And that's going to give us the combined number of moles of calcium and magnesium. It's not going to by itself let us figure out each one separately. But if we look at the second part of the experiment, then again, use the concentration of the EDTA and the volume to figure out the moles. And then that will tell us the number of moles of calcium. Again, use the mole ratio between EDTA and calcium. And then that tells us the number of moles of calcium. So if we subtract the moles of calcium from the total moles, that will tell us the number of moles of magnesium. And we want molarity. So what you do is just go back to the volume of the seawater that you used. It's 1 milliliter, convert to liters, and then you can calculate the moles per liter in the seawater. So the other thing we want to introduce in this experiment is the idea of uncertainty. So whenever you take any kind of measurement, there's always an uncertainty associated with any kind of measurement. So if you think about how we determine the magnesium ion concentrations, we have two measurements. It's the measurement we got from part 2, and we subtracted from the measurement we got in part 1. So that means when we're looking at the magnesium ion concentration, there's really two uncertainties. So what we do is we figure out S sub r. So we use the standard deviation from the first part and square that, plus the standard deviation from the second part, square that, and take the square root from the whole thing. So that's going to give us the uncertainties of both parts, and that's going to give us the uncertainty in our magnesium ion concentration. And then finally, we gave you at the beginning of the laboratory protocol a range of seawater concentrations of calcium and magnesium. So you want to compare what you got to the range that we gave you in the protocol. An important safety notes for today: be careful with all of the reagents. Make sure you wash thoroughly if any of the reagents contact your skin. Of course, you'll wear a lab coat, goggles, gloves, and shoes that cover the entire foot. The buffer we use here, it's very, very basic, and you wouldn't want to get that on any part of exposed skin. Make sure you read the labels carefully, and all of the usual laboratory cautions apply. So that is it for today. We will look forward to seeing you in lab.